repeated measures ANOVA. Okay, the key here is repeated. The key is not over time. So I'll just start out that way. You guys, I have to give you kudos for making it this far in this course. This is a big course. It's a lot of content. And I think it's very important that you not beat yourself up too much about failing, especially the first time through. When we're doing experiments, when we're collecting data, when we're running research, we're not always going to get it right on the nail the first time through. And sometimes we're going to have unexpected results because of things went wrong, or unexpected results because things are different than how we expected. And we need to learn to deal with uncertainty and failure. That doesn't mean we are a failure, that we can continue to grow and learn more. And with that pep talk, we're going to go into one-way repeated measures. This video is going to cover one-way repeated measures, and I'm going to do a separate recording for two-way repeated measures, ANOVA. So this slideshow, I think it goes through slide 35 for the one-way. So we're just going to do one-way. That means there's one way the data can be broken up. And the way we break it up is not independent groups, but repeated measurements on same subjects or same subject blocks. So here is our introductory example. There's going to be two of these, and these, don't skim over these. These are important. I find that students often have a hard time making this distinction. So here we go. This is the first example. Dr. Pearson is interested in determining whether the average man wants to express his worries to his wife more or less the longer they are married. The desire to express worry scale is administered to men when they initially get married and then at their 5th, 10th, and 15th wedding anniversary. So the questions are, to begin with, what is the repeated measures factor and its levels, and what is the outcome? And these are the things that can kind of get hard to distinguish in the beginning. So what is it we are measuring? We're measuring the desire to express worry scale. So the desire to express worry, the do is our outcome. And we are repeatedly administering it at different times. The repeated measures factor is time, specifically 5-year wedding anniversaries or 5 years of marriage intervals. So the levels are initially married, so 0 years, 5, 10, and 15 years. The repeated measure here is time married, and it has 4 factor levels. The factor is marriage time. The levels are 0, 5, 10, and 15 years. The outcome is the do. The outcome is the thing we are measuring. The repeated measure is how often or how many times that we're measuring it at. Okay, that's a longitudinal example. Longitudinal, when we're measuring things a long time, that's how I remember it. It doesn't have to be, it could be every 5 milliseconds on some other measures, but it is how the time increments we're measuring it at, if it's longitudinal. Repeated measures factors do not have to be over time. They are used anytime we are repeatedly measuring an individual, and they don't have to be the same measurement. So here is another example that is not longitudinal, not over time. Dr. Fairchild wishes to compare reaction times differences for 3 subtests of the Stroop test in patients with Parkinson's disease. So the subtests in the Stroop test are color, word, and color word. So they have cards where they're actually supposed to read the word, red, cards when they're supposed to say the color of the text, it's written in green ink, or color word, RED would be red even though it's written in green ink. I think. Don't quote me on this, but it's a test that has subtests. And I think that all of you have probably ran into measurement scales that have maybe a global score, but also have component or subscores, subscales. This is an example of a different kind of repeated measurement where we have different components, but all of those components are measured on a person. So each person has a color score, a word score, and a color word score. All 3 of those scores on one person. And the idea is that a color score on one person tells you something about their word score. and their color word score. They're not independent of each other on the same person. So if you know my word score is probably more similar to my color score than my word score and your color score. They're not completely independent. And it's that lack of independence that we're going to leverage and incorporate into our ANOVA, our analysis of variance. Again, these subtests can be administered one at a time, or it's common to have the items mixed together. So we might have a questionnaire that you answer a bunch of items, say 20 items, 12 items, and then at the end of the questionnaire, the scoring happens by rearranging them into pools or sets of items. And so I might answer 12 items, and then they might be scored into a mood score, a depression score, and an anxiety score, all subscores of the same questionnaire. And in that case, the items are given not block by block, but are interspersed with each other. They're not sequential one after another, they're combined. And that order can be random, it can be set, it can be alternating, but the idea is that those repeated measurements don't have to be separated in time or separated in order. But when we get down to it, we have a person has multiple scores, whether they are the same score at different time points or the same score under different conditions or different scores but still on the same person. Often that's because they're subscores, but it doesn't have to be. So here is a diagram that's showing we have person A, B, C, D, and E, and they're measured at time point 1, time point 2, and time point 3. In that case, time is our repeated measures factor. Time 1, time 2, times 3. But the people, in this case it's blood pressure, was measured. The blood pressure was measured at all 3 times. In that case, the outcome, the dependent variable would be blood pressure. The independent measures factor is time with 3 levels, A, B, C, whether that's morning, noon, and night, or week 1, 2, 3, or before, at the beginning of a class, after the announcement of a pop quiz, and after the pop quiz, but have multiple measurements of blood pressure on each subject. Same subjects, each time point. The second diagram is if we have the same people under different conditions. So we might have these people and we see how much chocolate cake they eat or rate how much they like chocolate cake. And then we might ask them to rate their taste or how much they eat or how much they like of caramel cake. And the same thing for lemon cake. So in this, it says taste score, if I'd read my slides. So maybe we have people giving taste scores for 3 kinds of chocolate cake. The key here is we have 3 measurements, 3 taste scores for every person. One is for chocolate, one's for caramel, one's for lemon. So they're different conditions. The order is not what we're testing. It's the condition or the topic or the flavor, but we have all 3 on each person. So those would be, instead of having measurements sequential in time, they are specific to something else, but we have multiple measures per person. So the design types, number 1 is we have the same outcome at different, on the same cases. So we have 5 people at time 1, the same people at time 2, the same people at time 3. So we have same people, same outcome, but different occasions. And this is probably, this longitudinal is what most people think of when they hear the phrase repeated measures. But I want you to kind of open up your brain to the other ways that you can have a design like this. You can have different outcomes on the same people. So this is the example where we had the same metric. Maybe it's on the same 1 to 5 scale, but we'd have maybe depression, anxiety, mood, sleep. We could have different subscores on the same metric, the same scale, measurement scale. And it doesn't necessitate that those have to be taken first, second, third. They can have the items interspersed, but we have different outcomes. The different outcomes, the different subscore titles are our repeated measures factor in that case, not time. The third is if we have different conditions. So this one, sometimes you can do all conditions to the same person. Sometimes you can't. So if we're teaching algebra and we have 3 different methods, pencil and paper, computer, group work, you probably can't teach the same algebra chapter multiple ways to the same person. So this is where we would do a matched design. And we talked about these back, it seems like forever ago, a lifetime ago, when we talked about paired t-tests. In a paired t-test, we matched people together and we gave person 1 this treatment and person 2 this treatment. So now we can just expand it. Instead of having matched pairs, we can have matched triplets or quads, and then within each set or block, we are going to randomly assign one of each treatment level. So we'll get some examples of this so that we can start putting some words to it. Key here, the design in a repeated measures ANOVA can be experimental, where you are the researcher is assigning the different conditions. It can be quasi-experimental, where students are already in classes. It can be field or naturalist, where you're totally observing. Or it can be longitudinal, and sometimes we call that developmental. Now, design type 1 here, where we have time points. Time points we usually label when we have times. We don't usually call time an experimental factor, because the researcher, although they choose which times to measure, the researcher does not have control to randomly order the time. 1 week is always going to be before 2 weeks is always going to be before 3 weeks. We can choose which weeks we're going to observe at, but we cannot rearrange the order. So because of that, time is not usually called an observed or an experimental factor. It's usually just stated as time, something that's inherently different, and we call those longitudinal designs. So benefits, doing a repeated measures design study. There's a big if you can do it, then bing, 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 that's a good thing. It's more powerful than an independent group because it controls between subject variation. In a way, each subject acts as their own control group. And that's what strengthens this type of research. That the error term, because of that, is often smaller. And the book and then the formulas kind of try to put that forth, but I don't know if it really comes out in looking at the math equations, if you're not like a really math geek like me. But that's where the power is gained. And that's because we factor out subject to subject variability. So we can say, what is the effective time? Or what is the effective condition after accounting for subject to subject variability? Because we usually know people are different. That's why we have to sample multiple people. And so we want to generalize to people that are different. And so we are able to factor out or extract person-to-person variability. So this is often called a within subjects factor or within subjects design. Now, the last couple chapters we've done on Unit 3, all of our grouping factors were between subjects factors. Gender applied to the subject as a whole, and it would be different from subject to subject. Within subject factors are ones that have multiple levels within a person. So in the longitudinal example, within each person, we are taking measurements at baseline, intermediate, post, and follow-up would be an example. Or within a subject, we're measuring them on sunny days, cloudy days, rainy days, etc. So we have different conditions or repeated measures within or on the same subject. It's more economical because of this increase in power, because we're able to factor out person-to-person differences. We need fewer subjects. If we were going to do a 3-group design on independence ANOVA and we needed 10 people per group, we'd need 3 times 30 people. But if we can give each person all 3 conditions, then we only need 10 people and we get 3 measurements per person, and we still end up with a sample size of 30 observations, even though we only have 10 people. So that's the power is increased. So if we have more than one repeated factor, so if we go back, when we did independent groups ANOVA, we did 1-way and 2-way. If we're grouping them by one factor, we said K equals the number of groups. But if we said if we're splitting our sample 2 ways, then we might have rows and columns, R and C, and then we have R times C number of combinations. That was the difference between a 1-way ANOVA and a 2-way ANOVA. And those were 1-way independent groups ANOVA, 2-way independent groups ANOVA. We can do the same thing with repeated measures. If we have one repeated measures factor, like just time, we would usually call that a repeated measures ANOVA, or just a repeated measures design. But we can also have 2 repeated measures. So we might be measuring 3 different subscales over 4 different time points. So we would have time and condition. That's 2 repeated measures factors. And often we'll call that a factorial repeated measures ANOVA. And just like we'd call a 2A independent groups ANOVA, a factorial ANOVA. When we don't say independent, it's assumed to be independent. Excuse me, if there's repeated measures, we better say that. The last kind of ANOVA that we're going to cover in this class is chapter 16. That's coming next. And that's where we're going to combine the independent groups and the repeated measures. And when we combine both between subjects and within subjects, we call it a mixed design, because we're mixing the independent and the repeated measure factors into the same study. And those are probably the most common in real life, because we have both things that we want to look at the same time. And plain repeated measures factor, factorial or multiple repeated measures factors, or mixed design ANOVAs, all of those, what we're doing different from the independence group ANOVA is that we have lack of independence, that we have some association or some correlation between repeated observations made on the same person, the same block, and we need to account for that in our analysis. And I think that it's important to say we're not just wanting to account for it, but we want to leverage it to make a more powerful test. So first, let's start with the longitudinal design. These are the ones where we have time as the repeated factor. We can answer questions like, do the measurements on an outcome change over time or under different conditions? We can also go further. We can say, is that a linear change or a quadratic change? Right now, we're seeing the number of cases in COVID-19. And you might say, in Logan, what is happening with the number of COVID cases? Last week, 2 weeks ago, last week, and this week. So there'd be 3 time points. And we can answer the question, has it changed over the time? As well as, has it changed linear, which is constant growth, or quadratic with increasing growth? You can answer, in addition, is it positive or negative change? That's just as important as what kind of change. And does change first increase and then decrease, or vice versa? How long does the change last? Is the change permanent over the duration of the study? Is the outcome the same at the beginning and the end of the study? So a lot of times in psychology, we'll see baseline, intermediate, post, and then an 18-month follow-up. And a common trend we'll see in something like the studies I've been working with teletrichomania, they'll see an initial decline from baseline to intermediate, and then a slower decline, intermediate to post. And then they'll see a small rebound or uptick to the post, the 18-month follow-up, for an example. So we can ask, is there a change? Where is the change? What is the shape of the change? And is it persistent, or does it rebound? So the researcher, again, I said this before, decides when and how frequently to observe the measurement, but time is not really considered an experimental variable because you cannot manipulate it. You cannot counterbalance time, meaning reverse the order for some people, and you can't randomize the order of observations. Time 1 always comes before time 2, always before times 3. So even though we have longitudinal factors, they're not really an experiment unless we add another factor that might be able to be manipulated or randomly assigned. Now, this is a big shortcoming of ANOVA. And this is part of my love-hate relationship with ANOVA. So I teach this class at least twice a year. And I believe in this class because it makes your roots, your foundations in statistics strong. But ANOVA by itself has some shortcomings. And this is one with longitudinal designs. It requires that your time points are equally spaced, or it treats those times at different time points as if they were equally spaced. So if we had baseline to intermediate is 2 weeks, and intermediate to post is another 2 weeks, say we had a 4-week spanning treatment, but then we have an 18-month follow-up. Repeated measures ANOVA treats them as if they're equally spaced. time points. And that may or may not be advantageous. A lot of times it's not. So if that's the case, if you have unequal spaced time points, ANOVA is not probably the best approach statistically. Instead, there are random effects, or sometimes we call them mixed effects models. These are also called multi-level models or hierarchical linear models. And I teach a whole course on this every fall. And here's a little plug for Psychology 7650. So if you have unequally spaced time points, really a multi-level model or a mixed effects model, a random effects model with regression base is going to be a better fit to that data and give you better power and more accurate results. So here's an example of the kind of way that we could look at a table of data that is repeated measures. This is what we call wide format. In a way, we have subjects 1, 2, 3, 4, 5. Each subject has its own row. And then in the columns, we have their score for month 1, month 2, and month 3. So if we look at the first person, their scores go from 1 to 3 to 6. They're increasing. The second person goes 1 to 4 to 8. Ooh, they're increasing even more. But the third person goes 3, 3, and then 6. Everyone has a slightly different pattern, but our question could be phrased, is there growth over time? And if so, is it constant linear growth? And if we look down here at the bottom of the table, we can see the margins that are the column means, and they go from 2.4 to 3.8 to 6.4. That looks pretty consistent with growth. Then if we look across each row, we have row means. So it kind of looks like our two-way independent groups of ANOVA. But instead of having each row be a group, each row is a person. And in this way, a repeated measures ANOVA is really a two-way independent groups ANOVA in disguise. But our cells in the middle are only n equals 1, which causes some complications if you think about it that way. So we look at each person. Each person's average is slightly different. The first person's average is 3.3, but if we look to the next to the last person, their average is 5.67. So there is variation from person to person. Some people might be inherently high, others might be inherently low. So we want to control for person-to-person variability, and after that, answer the question, is there any significant difference in the 3 time points, 1, 2, and 3? This next design is where condition is the repeated measures factor, and it looks almost the same. In this one, they've chosen to put the S1, S2, S3, S4 designations in the cells. Mostly the same. The thing is, 1 row per subject, 1 column instead of time point for each condition, and they're calling them treatment A1, A2, and A3. We're still going to have can do column means, row means, and the grand mean. That's what in the yellow light box at the bottom, the capital G, capital M stands for. Grand mean is always in that corner. Okay, simultaneous repeated factors. So we've already talked about longitudinal, where our measurements are occurring in time, one after another. And usually our main focus is what is the change happening over time. But we can also have simultaneous repeated measures factor. And that simultaneous is when those items are intermixed a lot of the time. If we're asking students to do tests on a computer, it's really easy to randomize hard, medium, and easy difficulty items, or different length recordings that they have to listen to and rate. Computers really make the simultaneous a lot easier than maybe in the good old days. So simultaneous means mixed or intermixed, one within another, during either an observational or an experimental study. So we might give a test where we're asking people to memorize words, and some of them are nouns, some of them are verbs, some of them are adjectives. And then we might have them memorize the list, and we might have them repeat it back to us. And then to score it, even though the nouns, verbs, and adjectives were intermixed on the questionnaire or the memorization list, then when we score it as if they were 3 different tests. Now, I said, if you can do it, a repeated measures design is more powerful. And it is if you can do it correctly. Now, one of the big benefits of intermixing items instead of having them in sets one after another is the idea or the concept, the phenomenon really, of fatigue effect or practice effect. So it has been shown time and time again that if you give people a long test, one of two things tends to happen. Either they get better and better at the items. This happens a lot at a math test. And so if you're giving this over a long period of time, especially, that they will kind of figure out maybe some patterns or some tricks, or for some reason they get better. It's probably more common when you're giving surveys that people will get fatigued, that at some point they will stop caring, they'll stop answering appropriately, or they'll stop answering altogether. And so if you always have the depression questions first and the sleep second and then the mood third, they're more likely to be accurate at the first and less at the end. And so if you have your items intermixed, then all three subscores are going to have the same degree of fatigue or practice effect to them. So it's a good idea to intermix your items to the ability that you can. It's not always feasible. I was on a study that was looking at validity of a autism knowledge scale, and they had their scale and somebody else's scale, and then they wanted to show that those gave similar scores, and then they had a different scale. I think it was HIV, which shouldn't be related to ASD autism at all. And when they gave the autisms first and the HIV last. Well, the HIV questions were most often skipped because people got sick of filling out this survey. It would have been a lot better to have had all those items intermixed. Sometimes we do have constraints. It's not always feasible. But here's an example where we're looking at, I don't even remember all of the technical things going on here, but we have lysine and aspirin. So two different conditions. And we have, in this case, they could give both drugs to each person, but not at the same time. It's not one you can intermix. So they needed to give one drug first, and then the second drug second. But what if one's helpful? Then you're going to get better, and they're going to be in a better spot for the second drug. What if we cleared up the problem? There's nothing left. Or what if it was harmful? They're in a worse spot to start the second one. So this is the idea of crossover. Well, that's carryover effect. When the effect of what comes first has some effect on what comes second, that's crossover effect. Carryover effect is, say we give them lysine first, and lysine's good stuff. When we switch to the aspirin, if aspirin's going to come second, lysine's effect might go on after we stop taking it. And so this carryover effect, we want to allow a period of rest or resetting in between, and that's called a washout period. And it could be that we don't give them nothing, but maybe we switch aspirin to lysine, boom, one day, but we don't take any measurements or analyze the data that comes for a little while after that, because we're going to allow the first phase to fade out and the second one to come up and establish itself. And so we might have a washout period to allow for that switchover. This is important, especially when time is in our main a factor that we're trying to study, when our research question is really about two different, say, drugs or two different conditions. Now, it's also important that we have not everyone in our sample have aspirin first and lysine second. So we'd want to split our sample in half and have the first half of our sample do lysine followed by aspirin, and the second half of our sample do the other order. So we want to have both orders available, and we want to have a gap in between where the data that's gathered for analysis. So usually the carryover effect is not interesting. It's spurious. So that's why we want to not analyze the data right after we switch. Now, how long should the washout period be? completely depends on the thing that you're studying, and no statistician is going to be able to tell you the right answer. You as the expert are going to know better. Okay. Okay. Say we had not just 2 drugs, aspirin and lysine, but say we had 3, or we had 3 different surveys, separate surveys that we couldn't intermix, that we needed to give one at a time. Or maybe there were 3 types of conditions. Like one day they came in and did a test in the control, and then the next day they came in, took the test in loud music or under supervision, and then the third day was something else. A, B, and C, we'll call them. And whether they have to be on separate days or separate weeks because of time constraints or the way that we're measuring things, say we can't intermix them. We can't intermix them. We don't always want to have everyone have the same order, A, B, C. So sometimes we would choose to randomly order. But if we have 3 components, 3 of them could be first, and 3 of them could be second, 3 of them could be third. But after we pick the first, there's 6 ways to order that. And we don't always want to give all 6. So there's another way that you can pick some of the orders, and it's often referred to as a Latin square. So we might have some do A, B, C, some do B, C, A, and some do C, A, B. So that would give a third of the people A first, B second, and C third. A third, each condition would have a third of the people having it first, a third having it second, and a third having it third. So that's another way to avoid carryover by counterbalancing. And it's called partial counterbalancing when we only have some of the orderings. But some is better than none, and we want to do it in a balanced way. So just like we might have a washout period when we switch conditions, we might want to have a run-in period after we've swapped. So not only do we want the prior condition to wear off, we want the new condition to kind of ramp up and stabilize before we take a measurement. So these are all things to think about when you're designing your experiment, if it involves repeated measurements on the same person. They're all concepts that need to be in the planning phases. And this is why it's very important that most new studies go through some peer review, whether that's to get a grant or a proposal in front of a committee, that we really kind of plan through these things. Because if we don't kind of think about what things could go wrong and come up with ways to avoid the issues, and we just go grab some data, garbage in, garbage out with the analysis. So you really want to plan carefully how you're going to collect your data before you worry, or at the same time you're worrying about how you're going to eventually analyze it. Another thing is that you can do is give distractor items. If you don't want people to have a strong learning effect, you could add other items in to kind of throw them off the track, so they aren't knowing what you're asking them about. Nothing is perfect. Even when you think you have the best design and you've come up with everything that could go wrong and you have all these contingency plans and things in place, things will go wrong. But we don't want to just bury our heads in the sand. We want to plan to do the best research we can. So we've talked about having each person measured under multiple time points or multiple conditions or multiple subscores. But sometimes even having different days, different time points, counterbalancing is just not feasible to have every person have every condition. There's just not that feasibility. And the next best thing is to do a matched design. Now, matched designs are inherently difficult because we're going to have to match on something or some things, and there are, by virtue of matching on these things, we are unmatching, so to speak, on all other things. So you have to know what's important to match on. Now, often with matching, we choose things like gender and age and education, these very easy to obtain measures. But often those aren't the important things. Things like family history and exposure and prior exposure, prior history, those things are more important. Thought processes, genetic makeup, and those things are less easy to get numbers on, and so we can't match on them. So I just put that caveat in there that if you're going to do matching, you better have a really good idea of what matters and the ability to capture those things, because it's not always very clear. Those things we want to match on, we often call confounding factors. They're things that are involved in or both the predictor and the outcome, both the independent variable and the dependent variable. But say we know everything that's a threat to validity, we know everything that's important, we're going to go ahead and do matching. So down here in my red box, I have 4 people in my sample, just for illustration. And say I could match them through the screening process. So usually, you have a screening process where you gather some information on your participants and enough that you can match them. Not just match them easily, but match them on things that are important to the discipline you're studying, your treatment and your outcome, your exposure and your outcome, your independent variable and your dependent variable. So what you do is take your subjects, screen them, decide whose matches. And these can be matches in pairs, in triplets, in blocks of 4. Usually that's as many as we do, but you could match them into groups of 20. But the key is you want to match them in groups where one member of each group will be assigned each condition. So in my little people, it looks like those little people toys down here, the 2 light blues have been matched together and the 2 dark blue have been matched together. So first I screen, match them, and then we randomize within each pair. So I would take the 2 light people and flip a coin or use a random number generator to decide the first one gets the red pill and the second one gets the green pill, whether they're placebo and control or lysine and aspirin, I don't know. And then you'd repeat that within each pair till you got to the last pair, and you'd say, okay, 2 dark blue people, one of you gets red, one of you gets green by the flip of the coin. So we are still randomizing, but we're randomizing within each pair or triplet. That way we can control for the factors we matched on. So we can control for age, control for sex, control for education. Now, this is one way to do it. Another way is to do a multiple regression where those are all covariates. I would prefer that way, but this is another way to do the matching. Matching, if you can match, it's great. The problem that happens in real life is we don't have a full understanding of what we should be matching on, or we don't have the capability of measuring the things we think we should be matching on. Okay, so this bullet here, let's see, that last bullet. When we go to analyze it, we treat members of the same pair, members of the same triplet, as if they were identical people. And this is kind of the stretch for the matched pairs design or the matched triplets design or matched block design, is we only can have the ability to match on a few things, and we're going to treat them as if they're identical. And that's kind of the catch. So we're going to treat those pairs, those partners, as if they were identical people, like identical twins and then some. So sometimes we use pretest during the screening for matching, but a lot of times researchers have too much faith in their ability to match. If you do this, you usually only match on 1 or 2 variables because it gets really complicated to find good matches if you're matching on 12 variables, especially if your sample size is 20. And you most definitely need to report in any write-up or publication what you matched on and how you did the matching, so people can judge if it was fair or not. Okay. I have a little plot here. It looks like I have 4 people in our plot. 2 pink, which are the treatment, and 2 teal blue, these circles are at the bottom, which are the control group. And we have, let's see, baseline, injection, 1 hour later, 6 hours later, 12 hours later. So right off the bat, if I'm looking at this, if I'm going to measure this with or analyze this with a repeated measures ANOVA, it's going to treat those time points as if they're equally spaced. And right off the bat, I can see 1 hour to 6 hours later, that's a gap of 5 hours, and 6 hours to 12 hours, that's a gap of 6 hours, which you might say, maybe that's okay. But from injection to 1 hour later, that's only a gap of 1 hour. And baseline to injection, we don't have any idea how long that period was. Who knows? But it's probably not 6 hours. And even if it was 6 hours, it couldn't be both 6 and 1 hours at the same time. So we're looking at some signal over time. And it looks like the teal groups have an initial uptick and then it comes back down. Whereas the hot pink groups see a very big uptick and then a slight decrease. So visual analysis, my eyeball test says the true treatment, has a bigger initial jump between injection and 1 hour later than the control. And that difference, the gap comes down a little bit, but that difference does persist out to 12 hours later. Okay, so for these repeated measures ANOVA, now we're talking one-way repeated measures ANOVA. I said it's a two-way independent groups ANOVA in disguise. So the repeated measure is like our within subjects factor, whether that's time or condition. But instead of having a second grouping variable, subjects are groups. And in that way, if we have 8 participants, that would be like we had 8 groups, or R equals 8. The only difference here is we're only going to have one measurement per group per time point because each cell would have sample size 1. But our hypotheses are the same in that we're saying that the means are the same. The means for treatment and control are the same at all time points, versus the alternative is that there's not the same. So if we think back to when we were doing ANOVA, we did the partitioning or a variance and also the partitioning of the degrees of freedom. Remember, we did the splits for the sum of squareds and for the degrees of freedom. We're doing the same thing here, but we're just splitting more times. So our repeated measure factor and our subjects factor are both going to split, but now instead of having a group by group interaction, we're going to have a repeated measures by subject interaction. So we're going to separate or partition our variance into 3 parts. We're going to take our total variation, our total sum of squares, and split it into 3 parts or 3 piles. We have our repeated measure, we have our subject, but now our interaction is repeated measures by subject. Notice in this equation, there is no sum of squares within. And that's because each cell only has one observation. There is no variation if you only have one observation. So there's no variability within cells. So instead, we're going to use that interaction between repeated measures and subjects as our error term. So these formulas should look fairly familiar. Now, when we did a one-way ANOVA, we did K equals number of groups. When we did two-way ANOVAs, we did R for row, number of rows, C for number of columns. When we go to repeated measures ANOVA, we're going to go back to K, but K is going to be the number of groups. Really doesn't matter which letter we use other than it'll look familiar, but K in this case is going to stand for number of groups. And so Kn is the number of participants per repeated measure factor. Now that should be the same. If we have 10 people at time 1, we should have all 10 people at time 2 and all 10 people at time 3. In fact, if we don't have all time points on all people, we have to throw out the people with partial data. And this is another big hang up that I have with ANOVA. First, it treats the time points as if they're equally spaced. And second, you can only use people with complete data. And in the last year or two, I've worked with a lot of people that do mice models, and they do a lot of repeated measures design because then they can get away with only having to train 10 mice because it might take them weeks and months to train these mice, and they've got to grow and they've got to order them. So they can only use 10, but then they can measure them 10 times. And it's like they had more than 100 mice to begin with if they can do a repeated measures design. And with mice, usually they don't, have attrition in that they fail to show up. However, sometimes they die. Sometimes they have little things in their brain and they pull them out and then you can't measure anymore. That's been something that I've heard people complaining about lately. So in that situation, if you don't have every measurement on a person or a mouse, they cannot be used in the analysis if you're doing a repeated measures type ANOVA. If you move to a multi-level model, here comes my plug again, Psych 7650, then you can use people with partial data. It's the benefit of that alternative approach. However, it's a lot more complicated and you got to understand this first. So here we have a formula that looks a lot like our within groups formula. We have the marginal sample size times each margin average minus the group average squared. Looks really the same. For subjects, we get the same thing. We have each subject's average minus the grand average, each of those squared times the row number, the number of repeated measurements in each row. And then there's the alternative formula. The top one, again, for both of these, for all these sum of squareds, the top one is the one that we usually use for repeated measure or for by hand calculations, and the bottom one is the version that's mathematically the same as the top one that the computer tends to use. And then we have the interaction, and I'll let you just peruse that at your own. So here we go. I have on this, let's see, it's my left side, the independent groups ANOVA. So we partition or divide up the sum of squared and the degrees of freedom, the total, into rows versus columns, rows versus within, between groups versus within groups. The repeated measures ANOVA, instead of having between and within, we have repeated measures, subjects, and the interaction. So the degrees of freedom follow very similarly. In both of these, when we're doing the independent groups, is the between subjects factor that we're trying to test. In repeated measures ANOVA, it is the repeated measures factor we're trying to test. That is the mean sum of squared that goes on the top of our F ratio. The difference is what we put on the bottom. With an independence group ANOVA, we put the between groups mean sum of squared divided by the within groups, between versus within groups. But with the repeated measures ANOVA, there's only one subject in each cell. So again, we're going to use that interaction term, subject by repeated measure, as the error term or the denominator term. It's different in this case. So generally, we ignore or treat as a nuisance the mean sum of squared of subjects, the between subjects variation. And that's because it's usually assumed that there is subject to subject variation, and that if we had a different set of subjects, it would be a different quantity, but it wouldn't be zero ever. There's always going to be difference in subjects, but the subjects we have is just a random subset of all possible subjects. And because of that, we ignore that mean sum of squared for subjects in the calculation of the F ratios. And again, if you have more complications, we can use the mixed effects ANOVA, mixed design ANOVA, or multi-level models. Okay, this slide is just chocked full of text. So let's see if we can get down to the nitty-gritty here. So the repeated measure by subject mean squared. This is the number that we put on the bottom of the F ratio. By itself, we usually don't care how big it is, but we're using it just for testing assumptions and for making our F statistics. It does have the assumption that we have a similar pattern over the repeated measures for all participants. And if everyone had a perfectly the same pattern, it would be 0. It's not going to happen. But if it's too big, we might have a problem. And the best way to kind of get a sense for is it too big is to do a line plot of individuals. And this is also called a person profile plot, or sometimes a spaghetti plot. And we will look at some of these. And if you watched the example walkthrough that I recorded before this, I went through some of those looking at if the pattern of the people are about the same. That's the major things on here. The better we can match, the smaller this gets. Sometimes we can, sometimes we can't. So here is the basic outline of a one-way repeated measures ANOVA summary table. So you'll notice it's very similar to the independent groups ANOVA, that our first column is sum of squared, degrees of freedom, mean sum of squareds, F, and then P. That's the same order of the columns going across, but the rows going down are slightly different. The first one here in the general format is the repeated measures factor. That's the thing we want to test, and that's usually the only one that gets a p-value. Now under that, I'm showing in blue the subject line. Now I said that the subject to subject variability it's there. We have subject to subject variability, but we usually don't want to test it. So because of that, if it shows up in an ANOVA table, it usually does not have more than those first two columns filled out. And in fact, in R, it doesn't show it at all because it's usually not of interest. Let's see, it's light orange here. Salmon orange. The error term. For repeated measures ANOVA, the error term is the repeated measures by subject interaction. And we use the sum of squared, the degrees of freedom, and fill out the mean sum of squareds, but we usually don't calculate an F statistic for it because we're assuming that there is some repeated measure by subject interaction. That's our error term, but we usually don't want to test it to see if it's bigger than 0 or not. And then there's often a total line. So we'll see some output in a second. Let's talk assumptions. There are always assumptions with every statistical model. Always. And all models are wrong. They never capture the complexities of real life fully. But some models are useful. And we are always going to have assumptions for those models, and usually we're going to violate them to some degree. But if we violate them a lot, then the model results are highly questionable. If we mostly meet the assumptions, we can usually depend on the results. So before you know whether to rely on your results, you better test your assumptions. And with repeated measures ANOVA, there are more assumptions than independent groups ANOVA. But the first few will look familiar. The first one is that we have random participants. The participants are not connected to each other. Now, with repeated measurements, we know that the repeated observations are dependent on each other and who they're taken on, but the subjects themselves are independent of each other. So I'm not going and getting everyone that lives in this house and everyone that lives in that house and making a sample size 12. And then we have two groups of 6 really making up our group of 12. Our subjects are independent of each other, even though the repeated observations are dependent on the subjects on which they're taken. ANOVA, this is another kicker, assumes that our outcome is normally distributed in the population. And sometimes things are skewed, not because normal is right, just because they are. And so if you have a non-normal distribution, repeated measures ANOVA doesn't work. Any guesses on what's a fix for that or an alternative strategy? You got it, multi-level modeling. So plug for 7650, multi-level modeling. You can have non-normal outcomes. You can have imbalance in your sample sizes. You can have people with incomplete data, and you can have unbalanced or time points that are not equally spaced in time. So all of those are assumptions of ANOVA. The normality one, we can kind of get away with that out because of the central limit theorem if we have sample sizes that are fairly big and equal per group, if we get groups. Homogeny of variance. Where have we heard this before? It's like every single t-test and ANOVA test assumes homogeny of variance. Every one of them. And how do we check homogeny of variance? Levine's test or visual inspection. If time is the repeated measure factor, then we want to have the time points separated equally in time. I said that a minute ago. And this is a new one. This is a good one. It's called, everyone say it with me, sphericity. It's like a sphere. Sphericity. I'm going to trip over it 10 times before we get through the rest of this recording. A related concept, which is easier to test than sphericity, is called compound symmetry. And that's usually what we actually end up testing. So because we know if compound symmetry is satisfied, it guarantees sphericity is satisfied. So it's easier to test it. And then if we pass, guaranteed. So that's usually what we test. Okay, so let's this new thing. Let's see. So we know how to randomly sample participants. Can't statistically test that. Just can have good sampling strategies in place. Normally distributed outcome. We might have a gut feeling on that or past research, and if not, a good size sample size. And the requirements, it says here, is that degrees of freedom for the interaction is at least 20, and the degrees of freedom for the interaction is a combination, we're going to see this in a minute, of sample size and number of repeated measurements. Homogeny variance, we already said Levene's test. Time points equally spaced or near equally spaced, that's just a planning thing. So this last thing, sphericity, we're going to have to look at. So informally, and I like informal, it says for all levels of the repeated factor, the independence is the same, or the correlation is the same. So that's the compound symmetry, says that we have the same correlation. So if we take time point 1 and 2, that correlation between those scores is the same as the correlation between 2 and 3. The variance is the same, but the covariance is also the same. Now, just like we have Levene's test to check homogeny variance, we are going to have Mauchly's test for sphericity. And Levene's test was based on an F test. F has 2 degrees of freedom. Mauchly's test is a chi-squared test. Now, if you think back when we were doing t-tests, we did Levene's test before we knew what an F test was, what the F was, with 2 degrees of freedom. Kind of hold on to this concept the same way, because Mauchly's is a chi-squared test, but we don't learn about what a chi-squared is till chapter 19, but we'll just go with it. So chi-squared is a statistic like Z or T that has 1 degree of freedom like T. And so the null hypothesis here for Mauchly's test is that we have no difference between all the pairs. So in other words, the null hypothesis is sphericity is okay. So it's like Levene's test that we want non-significance, because if we get statistical significance, it's saying we have significant evidence of a violation, and we do not want a violation, because that means that we probably should not be doing the ANOVA method at all. So it can be misleading because it tends to be either oversimplistic or oversensitive, but generally speaking, we're going to use it. We want to use Mauchly's test for all repeated measures factors. I got something in my eye. So there is a rule of thumb that says if the largest variance is 4 times the smallest variance, then that's a problem. Now, these variances are variances between pairs of repeated measurements, not each repeated measurement itself. If we're looking at variance at each time point or each condition, that's Levene's test. This is looking at pairings of time points, the differences. So here's a catch. You don't have to worry about Mauchly's test of sphericity if you only have 2 levels of the repeated measures factor. So if we're only looking at pre-test, post-test, that's only 2 time points. There's only 1 pairing. And Mauchly's sphericity says we have consistency between the pairings. So if you only have 1 pair, you don't have to worry about sphericity. It's a nice thing. So if K equals 2 repeated measurements, you don't have to worry about Mauchly's test because there's no such thing as violations of sphericity. So usually I said we test sphericity by, not directly, but kind of through the back door, around the way, through compound symmetry. So compound symmetry is a little bit stricter than just sphericity. So it says, compound symmetry says we have homogeny of variance, so it tests homogeny of variance at the same time, homogeny of covariance, and additivity. So compound symmetry is all 3 of those components. And we're going to talk additivity on another slide. So homogeny of variance says we have the same spread in all of the time points. That's part of sphericity. And it also says we have homogeny of covariance, looking at the pairs. Most software doesn't assess that directly. It just does it through compound symmetry, and as well as additivity. So if we were to make a matrix grid of all repeated measurements, independence says that the variance of A is one value, the variance of B is another number, C, D. The variance at each time is the same. Notice these diagonals would be the same, but the covariances or the correlations are 0. So that's why there's zeros off the diagonal. And if this is a little too much, don't worry too much about this. But this is one way to display a variance-covariance matrix. So independent says all pairings have 0 correlation. Compound symmetry goes further and says they're not 0, but it goes on to say they're all the same. All pairings are the same. So all these off diagonals would be the same number. Okay. Additivity. So we said that compound symmetry, which is a little stricter than sphericity, says we have homogeneity of variance, homogeneity of covariance, and additivity. We're very friendly with homogeneity of variance. Homogeneity of covariance is looking at the pairing of time points or conditions. Additivity is a little easier to look at on a plot. It's looking at how consistent is the pattern between people, across people. And I think it's best to look at this with a plot. Let's see, I think there's one on this next slide. So assessing assumptions. Some of the assumptions like independence of subjects and equally spaced time points, there is no statistical test for, but there are some that we can use for the other assumptions. Homogeneity of variance, we can use Levene's test. There's also Bartlett's test, but usually we'll use Levene's test. In R, we use the CAR package Levene capital T test. We can do sphericity / compound symmetry with Mauchly's test. And this is we can also construct the variance covariance matrix and look at all the different pairings. But it's also built into the ANOVA 4 package. Yay, AFEX. And additivity. There is a test for additivity by Tukey's test, but usually we want to look at the plot. And additivity is okay if the plot, when we have one line per person, are mostly parallel. Not that the lines are straight all the way across, but they're all parallel. Okay. Yes. So what happens if we fail some assumptions? Well, sphericity can be violated. If told you I'd stumble on it. If sphericity, you guys say that 10 times fast. If sphericity is met, if it's okay, there are 5 different options to proceed. The most often recommended is standard univariate F test, and that's what we're going to learn. The second is trend test, if a trend is what you're looking for, of course, and usually this is trend over time. Multivariate tests, and these are MANOVA, are not recommended in general, like ever anymore. If anyone asks you to run a MANOVA, run for backup because you'll want to defend your criteria not to do a MANOVA. People that were trained further back in time, we'll say, we're not going to say older, but might be more familiar with and tend to go with a MANOVA, but generally they're not as powerful. Now here in red, it says use maximum likelihood procedures, highly recommended. And when we say maximum likelihood, these are the mixed effects regression or multi-level models that I teach in 7650. There's another plug. And you can also, it's lower power, but you can use a non-parametric test like Friedman's test, which we're not going to dive into, but there are some of those. So that's what you can do if you have sphericity met. Yay! What if sphericity is violated? Boo! What if your Mauchly's test says, hey, dude, you got a problem? Well, there are some band-aids we can put on, some corrections for sphericity violations. But generally, if we have violated sphericity, we should do one of these adjustments. Now, I'm not a really huge fan of these adjustments, but it's better than doing no adjustment. The maximum likelihood procedure is definitely what you should go with instead. You still can do a trend analysis. I would make sure to adjust your you're up with an epsilon adjustment. That's the next slide. Multivariate tests, again, are less recommended in most cases. The MANOVAs we wouldn't suggest. But maximum likelihood, multi-level model, they are great. Even if you violated homogeneity variance, even if you violated sphericity, Multi-level models, these maximum likelihood mixed effects models, are a lot more flexible. There's no sphericity assumption, there's no homogeneity variance, there's no equally spaced assumption, there's no balance assumption. They have very, very few assumptions compared to the ANOVA. Again, ANOVAs were developed in agriculture where they had a lot of control, not a lot of attrition. They could randomize everything. They have a lot of these assumptions generally met. When you move to human subjects, not always the case. So non-parametric are also available. So trend tests, not usually recommended with violations of sphericity because they can be inaccurate, type 1 error, but generally it's okay with trend tests, even if the F test is not accurate. Trend tests involve doing pairwise comparisons and looking at the shape, whether it's linear or quadratic over time. We're not going to get too much into this. The book does a little bit. Here's a huge slide. Oh my gosh, I can't even do way too much on this slide. Okay. Oh my gosh, these slides. We're going to just get through these two. We can do it. We're almost there. I think we have 3 slides left. We can do it. Okay. Here's the idea. If we have violations of sphericity, that means our tests are too liberal and we need to adjust. And the way we adjust is by changing downward, making smaller our degrees of freedom. Now we've done something similar to this on the t-test. Remember way back when we had matched t-tests and we had to do the pooled or the unpooled variance. Oh, they weren't the paired t-tests. They were, anyway, we had to decide if we were going to do degrees of freedom that were between this and that. They come out to a decimal number. Same thing happens here. In these adjustments for the F test, what we do is we take our degrees of freedom and we shrink them. We shrink them by timesing them by a number that's between 0 and 1. And different people have come up with different suggestions by how much we should shrink those degrees of freedom. Generally, the worse we violate the sphericity, the more we should shrink them. But exactly what relationship to the violation and the shrinkage is not been ironed out because there is no one right answer for every situation. So lots of people have published their take on it. And again, no one method works better than another across the board. But I would say the most common, especially in psychological and education, that you're going to see is called the greenhouse geyser epsilon. So all of these methods, the lower bound, the greenhouse geyser, the Hunfeld, there's a bunch more. Those are the ones that are most common. All of them create an epsilon based on your sphericity test. They take sphericity test and they decide what epsilon should be. Epsilon's less between 0 and 1. And that epsilon is what you times your degrees of freedom by. And it makes your degrees of freedom, say our epsilon comes out to be 0.5, our degrees of freedom instead of being 4 would then be 2. In that case, whole number. Doesn't usually happen that way. So down here at the bottom of the slide, I have listed from most to least conservative. So the lower bound estimate is very severe. Hunfeld is usually not, it's too conservative. So usually that's why people go in the middle with the greenhouse geyser correction. It tends to underestimate epsilons if it's close to 1, but it usually does a pretty good job. So that's those last two on there, the epsilon, greenhouse geyser, and Hunfeld are the two that are in the AFEX package are going to give us. I very rarely ever see the lower bound used. This next test is about MANOVA. The only thing I'm going to say there is it's less powerful, avoid. That's all I'm going to say. Okay. So maximum likelihood, yay, woohoo! These are the mixed effects, multi-level or hierarchical models, all mean the same thing. It's the wave of the, not just future, it's the wave of the present. That's why this class 7650 that I teach every fall, once upon a time before I was hired here, it was only taught by Jameson Fargo, our executive dean, every other year, and he might have 4 students. I've taught it every single fall for the last 4 years, and we generally have 15 to 20 grad students and usually several faculty auditing it. So there's a plug, take more stats, definitely that one, because you don't have to follow compound symmetry or sphericity. They're a lot more flexible. I'll leave it there. So Here's a little blip at the bottom box that says the sample size. So your sample size has an effect on how much your violations of sphericity can have. So if you have a large sample size, doing the correction only has minimal effects. But if you have a small sample size, you're more likely to reject or find violations of sphericity, and that correction could be really harmful to your results. So if you have a small sample size, you might not want to do your correction, your greenhouse Gaussian correction, because it's going to wipe all your significance out, similarly to the Bonferroni correction. So just a side note. Told you, got 2 more slides to go. Last thing, effect sizes. So when we did effect sizes for ANOVA methods, when we did t-tests, we used a Cohen's d, but with ANOVAs, we used an eta squared. And when we did one-way ANOVA, we just had eta squared. There was only one eta squared. Sometimes it's called the ordinary eta squared or the generalized eta squared, but it's just eta squared. When we move to two-way independent groups ANOVA, you can have the ordinary generalized eta squared, but you could also have a partial eta squared. When we move into repeated measures design, in the same way, you can have a couple different eta squareds. Good news is there's formulas on our formula sheet. Most of the time, the software is going to give you the correct one. Usually, if we're looking at the repeated fact measures by subject interaction, if that's very small, meaning we have fairly parallel lines in our spaghetti plot, additivity's met. Usually, the partial eta squared is the most appropriate one to go with. But if we have a lot of crossing over of our lines, then we want to go with this bottom one, this ordinary eta squared. I am a big fan of publishing both of these. If you're going to publish an ANOVA results, I think it's a really good idea to publish both. Granted, if someone has enough of your data, if you've published reproducible, transparent results, they should be able to get both of these based on your numbers, but it's a lot easier if you're doing a meta-analysis or a lit review if someone's already typed them out for you and done the calculations. So just like with the ANOVAs for independent groups, we said eta squared, easy formula, people use them, but really we ought to be doing these omega squareds, but their formulas get really complicated really fast. There you go. I don't see this catching on yet, but you might see it in your career that people move from eta squareds to omega squared. The interpretation is the same. I don't think that it's not really a pressing issue right now because usually these numbers end up being pretty similar within like 0.01 decimal places. So that's why people haven't gotten too excited about making the switch. Whew, we made it. Okay, I'm going to stop this recording on the one-way repeated measures ANOVA. Go ahead and get it processing and uploading to YouTube. And then I'm going to record another one on factorial or two-way repeated measures ANOVA. And maybe tomorrow I'll get your chapter 16 on the mixed design ANOVA so we can get this all out the door. So hang in there. We're so close we can taste it. Just 2 more weeks left.